All right. We've introduced the idea that there's this math, quantum mechanics, based on a bunch of calculus stuff that we can't really do, that will allow us to, in essence, predict in a probabilistic way a lot of stuff about how atoms behave. We'll be able to predict energies of the electrons, the arrangement of the electrons, all kinds of fun stuff like that. That's the sort of stuff that's most important to us. But it'll give us lots of other information too. But one of the big issues is that, of course, is it's as I say, it's probabilistic. It doesn't give us exact values. It gives us percentages, likelihoods, okay, of knowing certain things. Okay. For our purposes, what turns out to be really important is the square of the wave function. The square of the absolute value of the wave function gives us a what we call a probability density. Okay? These are graphs for a hydrogen atom. These are graphs of the probability density. That is the likelihood of finding an electron in or around the hydrogen atom. You can see that the probability increases as we get closer and closer to the nucleus. There is a node at the nucleus itself where the probability drops to 0. But if what we're interested in is sort of these contours, these regions where we say, where do we have 90% of the chance of finding the electron? Because what we're going to do is we are going to define a volume of space where we have a 90% chance of finding the electron, and we're going to call that an orbital. So an orbital is a region of space, a volume of space, because these are all actually three-dimensional. This is like a slice through a hydrogen atom. So here we encompass 10% of the likelihood, 50, 90%. So this circle represents a slice through a volume that encompasses 90% of the chance, 90% of the likelihood of finding the electron with a given energy. So that's what we call an orbital. Now, this is similar to our ideas about orbits. Remember we said the electrons had specific orbits that they had to be in. Each orbit had a specific energy. Well, if you take that idea of orbits and you try and, or regions of specific energy, and you try and calculate that based on this wave function idea, that's where you get these probability plots. So the math that drives this, the math that is represented by this wave function, takes a few integer values and spits out these plots, these probability plots. So you can say, what's the probability of finding it here, 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 and it'll give you a number for each region, and you can get these probability contours. Now, what we want to do is we want to convert that into, or if we did that in a three-dimensional way, because we'd want to plot this in 3 dimensions on an x, y, z coordinate axis system. The lowest energy, that sort of n equals 1, the principal energy level, that lowest energy that we looked at, we've seen diagrams where we say, hey, in the Bohr model, we had this line that represented the lowest energy. We called that n equals 1. And then we said, oh, we can have n equals 2, 3, 4. And we've been doing work with electrons dropping from n equals 3 down to 2 or 4 down to 2 in the labs that we've been talking about, right? So all of those orbits that we're used to thinking of, all that orbit stuff that you probably learned about in junior high, where, the first circle can hold 2 electrons, the second one can hold 8. Well, that's all wrong. It's not the best way to think about this. And I'm actually simplifying stuff too. There are more complex, better models, but we can't really deal with those because of the math required to deal with them. So as you go further in your scientific career, you will learn better and better models that typically require more and more advanced math, but they encompass greater and greater fidelity to the real world. So what we want to do is we want to say, okay, what does this look like in the sense of, if I think of an atom and I have a nucleus as a tiny, tiny point in the center, the first energy level looks like essentially a sphere. Okay? So here's my x, y, and z coordinate axis system. And if I take this and I sort of start it going here, you can see it's essentially just a sphere. It's a spherical volume of space that encompasses 90% of the probability of finding an electron. For a hydrogen atom, well, for all atoms, this is the lowest energy orbital. Okay, we call this the 1s orbital. Okay, and we'll talk about what those numbers and letters mean in a few minutes. But this is a solution to the wave function that gives us the lowest energy that an electron can have in an atom. And it's now not a circle, it's not an orbit, it's a volume of space. And we don't talk about, well, where is the electron inside here? We don't know. That's not what this information we can get. What we can get is the probability of finding the electron, not where it is or how it's moving around inside here. It is there, it does move around, but there's no way for us to know exactly how that's happening at the same time. We could know where it is, we could pin it down, but then we wouldn't know where it's going. Or where there's some things we can do to figure out how it's moving, but we don't know where it is. So there's apparently fundamental limits to how well you can know those two things. Now, that was one solution. And the wave function is a kind of math that has multiple solutions. You've seen equations where you can have more than one answer, like quadratic equations could have two answers, two zeros. Well, the wave function is one that can have lots of different answers, lots of different solutions. And each solution represents a certain energy that an electron has inside the atom. So the next solution, is again, has this sort of spherical shape. Okay? If this is my 1s, then the next solution, the one that has the next lowest energy, is n equals 2. Sort of like the second energy level. But there's some interesting stuff that comes out here in the wave function, and this is why the wave function and this kind of math is way better at explaining properties of atoms, because it gives us a better picture of what's actually happening. The second energy level is not one place or one energy that actually holds 8 electrons. It's actually split into different regions, different orbitals. The 2s orbital is again a sphere, but it's a sphere that now has a node in it. Okay? This is a spherical nodal surface in the middle. If you imagine sort of that shape, that rind, a sphere of probability, or a sphere where we're likely to find the electron, there's a node in the middle. Remember when we were talking about the drums, or when I drive at higher energy and I have to put more energy in to shake the spring, and I add more nodes? That's what we did. Okay, this was the lowest. Okay, just that center just at the nucleus and outside here, and now I have another node inside here. And this is a spherical nodal surface. But there's another solution that has a nodal plane that runs down the middle of the thing and creates this dual-lobed structure. So, remember when we were shaking the spring? Because this is a really good question about the positive and the negative values here. And if you imagine for a sec the spring, and think about it when I had the big spring when it had a wave like this, okay, where it went down, hit the node, and went up. Nodes are always inflection points, points where the phase changes from up to down or vice versa. Positive and negative simply describe the phase information here, whether it's up or down. Negative is still probability density. The electron is still going to be there. It's just a mathematical way that we can represent, hey, this amplitude is positive versus negative, but both positive and negative represent probability, likelihood of finding the electron. It turns out that this positive and negative, super important when you start to bring two atoms together because of the way they interact, positive versus negative. But for our purposes right now, positive and negative aren't super important. What's important is that we recognize that there will be opposites, and at the node the phase changes. Okay? So 1s, lowest energy level, 1s, a single orbital. Second energy level, we've got this s orbital. Okay, it's that same sort of spherical shape, but it's got a node in the middle. And then we have this 2p orbital. And the p tells us that it's a different shape. It has a different node. It's got this nodal plane down the middle. Now, when I look at this, I say, okay, that has a double lobe sort of shape on the x-axis. Well, why is it on the x-axis? Why not on the y-axis or the z-axis? Why does it have to be like that? And the answer is, it doesn't, because it's actually what we call a degenerate orbital. This 2p really is a set of 3 orbitals, 3 regions in space, 3 volumes around the nucleus where you can have electrons. So the p orbitals we have one on the x, one on the y, and one on the z. And really, it's all 3 of these. Okay? Not combined, they're each a separate orbital. But when I say 2p, you need to think, oh, p orbitals, those are the ones that come as a set of 3 that are all equivalent. I can't really tell them apart because it's just a rotation in space, x, y versus z. But it does have important impacts for looking at how the electrons are arranged in the atom. Because remember, these are the regions in space where we can find the electrons. This is a volume where we are 90% likely to find an electron of a given energy.
Does that have original symmetry to the point where you could rotate it in any direction and it's still the same? Not on just a certain axis?
Yeah, well, they're not spheres. So these volumes aren't spherical. They taper down like that.
But it seems like they're centered.
But they are centered on the origin, yes.
Are you going to talk about the antinode?
Yes, we will. We'll get there. So the idea, if we look back for a sec here, right? Antinodes are just places of peak density. So the antinodes are just places where the density peaks. Yeah. So that's just like the highest amplitude, the greatest probability. The nodes are really the important part for determining the shape and stuff like that. Antinodes are just points of peak density. All right. So we saw the p orbitals. All right. So I said briefly that the math that drives all this, the actual calculations, all that stuff, are very complex. It's calculus stuff that we can't do. What's interesting is that the calculus itself is controlled by a few 4 integer values. So we stick these integer values into the math, and they spit out these complex pictures. So the integer values we can learn about. So the integer values are what we call quantum numbers. Okay? And quantum numbers come in, some of them we already know about, and some of them we don't know yet. But we will shortly. N. N is our principal quantum number. N represents the energy level of the Bohr model. It gives us sort of, if you think of a quantum number as an address for an electron, which is a good way to think about it, the principal quantum number is the city that it lives in. Okay, that's like your city, or if you want to think a little larger, your state. But yeah, city. I like city. So the principal quantum number is your city. N equals 1. That's Berkeley. Okay, N equals 2. That's a little further away from the nucleus. That's Oakland. N equals 3. A little further away from Oakland. That's Hayward. Okay, but yeah, these N values represent sort of general energy levels. They're the Bohr values, the Bohr energy levels. And so N 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. Principal energy level. Then the next thing you want to describe is, well, what street do I live on? Okay, what street do I live on? And the street is going to be your L, okay, your L quantum number, which is called the angular momentum quantum number. Yeah. Angular momentum, right? Yeah. Is it not saying? Did I put it down? Okay. Yeah, it should be on there. And I've done this a lot. I should have this memorized, don't you think? Yeah. N is the energy level. L is the angular momentum quantum number. And that describes the shape of the orbital. So an L is equal to 0, we get that S shape, that sphere. Okay? Now at higher energy levels, the spheres have more and more nodes, but they still have the same basic shape. They're still spheres, but with nodal surfaces inside them. Sort of like if you imagine a rind on like if you have like an orange, you have that outer rind and the white pith part, and then you have like an inner coating on the orange. As you go in, there are different levels. In between, there's different surfaces. Those would be like the nodal surfaces. So the outer part is like a shell all the way around in a sphere. And then there's a point where the probability drops to 0 and another shell. Okay? So that's the S, is that sphere. P orbital is when L is equal to 1. When L is equal to 1. That's what we call a P orbital. Okay? So L equals 0, we call that S. If L equals 1, we call that P. And P is that double lobed shape. But then, you can get more complex ones with more nodal surfaces, more spherical nodes in there. You can have L equals 2. And that's what we call the D orbitals. D orbitals, we call those, we give those the number D. Or letter D, I should say. And they are even more complex still with lots more nodal surfaces. They are off axes. You get all these crazy shapes. Okay? And then we'll go all the way up to L equals 3, which is F. I call that F. And you can go L equals 4 for G and L equals 5 for H. Those things exist. They are because they're just regions in space around the atom. So they do actually exist. So the angular momentum quantum number is an integer value that you stick into the math that will generate this picture. It represents the angular momentum of the electron in that orbital, which is not meaningful to you. What is meaningful for us and what's important for us is that this L value determines the shape of the orbital. Okay? Now, each orbital shape, each L value, comes as a set of degenerate orbitals, a set of orbitals that all have the same energy. So L comes as a set of 1, 2, 3 values, 3 orbitals. Each one of those, this is like naming the house, your street number. So we said N was like the city, L tells us what street, M, okay, or M sub L tells us that's like the house address. Like I live at 1765. So that tells me one of the 3 orbitals that are the P's, or, because there's 3 houses on the L equals 1 block, on the P block. There's 5 houses on the D block. And there are 7 houses on the F block. So here this M is plus minus 1. One of these is plus 1, one of these is minus 1. And there's some math rules that we can use to help us figure this stuff out. Yeah. M describes, it's the, all of a sudden I forgot the name. Yeah, the magnetic, no, not magnetic spin. Yeah, the magnetic quantum number. Yeah, spin. MS is the spin. Magnetic quantum number. That's the one that tells us essentially the orientation in space. This tells me, is it on the x-axis, the y-axis, or the z-axis? Okay? How is it oriented in space? That's what the M value tells me. Okay? And then there's another number that we'll talk about in a few minutes that tells you what room in the house. It's like Harry Potter gets an address. It doesn't say, Harry Potter at, at Privet Drive, Little Whinging. It says on the floor, hut on the rock, the sea, whatever. It tells specifically exactly where it is. So we do the same thing for electrons because each one of these orbitals can hold 2 electrons. Each orbital can hold 2 electrons. Okay? So, when we are talking about where an electron is, if we want to specify its address completely, we have to give 4 numbers. The N value, the principal energy level, the L value, the M sub L value, and then the M sub S, the magnetic spin quantum number. All right? M sub S, we call it the magnetic spin quantum number. Now, these variables, these numbers, are mathematically related to each other in ways that are very simple. Okay? You can see in this chart, we have a particular set of, how come there's no P, D, or F for n equals 1? And how come n equals 2 doesn't have D or F? And how come n equals 3 doesn't have F? Well, it turns out that when you go through and solve the wave function, you can't get a solution with this set of variables. And there's some math we can use, some simple math that we can use to describe how these things relate to each other. So n has to be integer values starting at 1. 1, 2, 3, 4, 5, integer values. Now, the L value is equal to n, what the hell? Sorry. So it goes from 0 to n minus 1. Integer values from 0 to n minus 1. That's what I was trying to write. So it goes from integer values from 0 to n minus 1. So if n is already 1, 1 minus 1 is 0, so we only have the s orbital. Then if you have an n value of 2, you can have 0, and n minus 1 is 1, so we can add the p orbitals. And if you have an n of 3, then you can have 0, 1, and 2. And 2 is where you hit the n minus 1 value. Questions?
So is there any limit to the values of n?
Theoretically, no. Practically, yes. At some point, the electron is so far away, it's no longer really attracted to the atom, and it floats away. So there is a practical limit to how far you can go.
So we're saying L when n is 1 is 0?
It has to be 0. It's the only orbital you can have.
So it can't be negative.
It can't be negative. It can only go from 0, integer values from 0 to n minus 1. So if n is equal to 2, if you're in the second energy level, you get an s orbital, and you get the set of 3 p orbitals. Because you can have, at this energy level, right? So let me rewrite this a little bit. Here, right, we said L is equal to, from 0 to n minus 1. Here, n minus 1 is equal to 0. So you can have just 0. In this second row, for n equals 2, here, you have n minus 1 is equal to 1, so your L can be 0 or 1. You get an S and the P's. And then here you say, okay, n minus 1 is equal to 2, so my L can be equal to 0, 1, or 2. Okay? So as your energy levels get higher, there are more and more regions of space where the electrons can be at that energy level.
Why is L always
Because that's the way the math works. And there's no other way I can explain it to you at this point. So when you learn the math, you'll see that the solutions to these equations demand eigenvalues and eigenvectors, and they're a specific class of solution. That I can say words that won't make any sense to you. So I can make them up, but I'm not. Are we going to what? Yeah, we're going to spend time talking about this. I mean, this is the first shot, but you'll want to go through and read the book and watch this lecture again, and you're going to need to know how to do these things. When you'll see the homework problems, you'll see what you have to do. Okay? Now, next step. Each one of these is higher and higher energy, right? The higher the energy level, the further away from the nucleus, the more energy the electron has. Okay? So when we're looking at our hydrogen atom, we have this nice, simple progression. This is a hydrogen atom energy level diagram. Here's my 1s orbital. Remember, each orbital can hold 2 electrons. Then my second energy. Now, for hydrogen, it turns out that the 2s and the 2p's have exactly the same energy, which is why the Bohr model worked so well for hydrogen. Because the 2s and the 2p's have the exact same energy values. And then here's a third energy level, and lo and behold, once again, for hydrogen, 3s, 3p, and 3d all had the same energy level. Because there is only, when we're looking at a hydrogen atom, you get these energies to be the exact same. And in fact, adding more protons doesn't change that fact. But it does change the spacing. If I take and add some more protons here, if I look at ions, so each of these things has just one electron. Here's hydrogen. This is a helium ion and a lithium ion. You can see that the spacing changes. Here's my hydrogen's 1s to 2s. Look at the lithium 1s to 2s. Adding protons deepens the energy well. Means that to go from 1s to 2s is a much larger jump in helium than it is in hydrogen. And to go from 1s to 2s is a much, much larger jump for lithium. The more protons you have in the nucleus, the stronger the electrons are attracted, the more energy it takes to cause them to jump up. Okay? This is driven by the attractive force of the positive protons for the negative electrons. That's what causes this change in the energy levels. More protons, greater attractive force, harder to pull the electron away. Yeah. So, if you add protons to the nucleus, it causes a greater attractive force for the electrons. More positive charges, more protons, cause a greater attractive force. The more charge there is, the stronger the attractive force, the harder it is to pull the electron away, the more energy it takes for an electron to jump from a 1s to a 2s. Okay? 1s to 2s, or from 2 to 3. That spacing changes too. The spacing gets deeper. You imagine, I like to think of it as sort of an energy well. This is attractive force, and I have to pull it out of this well. The more protons you have, the deeper the well is. The more work you have to do to pull the electrons out. No, the distance, this isn't distance, this is energy. Okay, so this is actually energy. You can think of the well as getting steeper. Yeah.
So when you add protons to the nucleus, it creates a greater electronic charge. So then when they're bonding with other elements...
Let's not worry about that yet. We'll get there. We will. We'll spend a lot of time talking about it, and it is super important. Okay? But right now we're just talking about electrons within one atom. Because to bring in another atom adds a whole other layer of complexity.
I was confused about the whole well analogy.
Okay, so here's what I like to think about. The electrons are the water in the well. The deeper the well is, the more work you have to do to pull the water out. Okay? Does that make sense, sort of? So the more protons you have, the deeper the well gets. More protons in the nucleus. Okay? So for different elements, they have more protons. That's what makes one element different from another. So the electrons are pulled on more strongly. Okay?
So it just takes more energy to knock them up. I mean, down.
For them to jump up. And they'll give off more energy when they drop in. If I drop a rock down a really long well, it'll make a big splash. Versus if I drop a rock down in a well that is very shallow, then it will just make a little splash. Okay? Okay. So here we had 2 protons versus 3 protons. More protons, greater attractive force, bigger separation of the energy levels. Okay? Now, let's make it crazy. Here's what happens if we start to add electrons. Okay? Here, all right, here is my hydrogen atom, 1 electron. Notice that the second energy level, the S and the P are the exact same. Third energy level, S, P, D are the exact same. Now let's look at a helium. Okay? How many electrons does helium have? 2 electrons. So adding an electron causes a split in the energy levels. A split within an energy level. The 1s and the 2s are now no longer the exact same energy. The electrons, the multiple electrons, even though both of those electrons are in the 1s orbital, the fact that they are there causes additional interactions, repulsions, that cause a split in this energy level. And that split is caused because the S and the P are shaped differently. So they have different interactions with the electrons that are down here in the 1s orbital. And then you can go further. Lithium has how many electrons? 3 electrons. And the split gets bigger. The more electrons you have in your atom, the greater this orbital splitting becomes. The greater the difference between an S, a P, and a D is. So the more electrons we add, from 2 electrons to 3 electrons, the greater this split becomes. All of this stuff is important because what we want to be able to do is describe in order how do electrons fill up an atom. No, I don't. I'm sorry. I can try and come up with one. Essentially, really what's happening is the more electrons there are, so if you think about our house analogy, with the quantum numbers are a house, right? The more siblings, the more electrons you have in the house, the more interactions there are, the greater the separation in their rooms that you want. Like if you have a lot of kids, you want their rooms to be further apart so they interact with each other less. So they split the rooms apart the more children that are in the house so that they see each other less and so they'll fight less. I just made that up on the spot, so don't hold me to that one.
Helium only has 2 electrons. Why does it have so many?
Remember, these are regions in space.
So that
These are volumes in space that exist for everything. Well, we'll learn some rules about where they're likely to be because they're going to start at the lowest energy. That's going to be what we call their ground state. We know, however, that we can excite them jump up, right? Now, think about this. For hydrogen, remember we only saw a few lines. Because look, every single one of these is going to be the exact same energy. So when an electron drops from here down, it doesn't matter if it's in the 2s or the 2p, it drops with the exact same amount of energy. Helium, what do we see? More lines. Because look, the 2s and the 2p are a little bit different. Now they're pretty close. Those lines are going to be very close together. They're going to be similar colors. But you can jump from here or from here, and you'll get different spectral lines. And again, then you have these 3. Now you got 1, 2, 3, just a little bit apart. And again, 1, 2, 3, that's 3 lines real close together that you can get when they drop down. Okay? And so the more electrons you have, the more of these energy levels it's likely that you can jump up to. Okay? And in fact, it's even a little more complicated than that because remember, we're talking about energy level drops down to n equals 2. So you get 1, 2, 3 down to this one, and 1, 2, 3 down to this one. And then you have a little tiny one in between here. So there's a lot of different, the more electrons you have in your atom, the more complex those spectrums become. Like you saw neon, crazy number of little red lines, right? Because you're talking about splits, these splits in here becoming different, and then a lot of drops down between 1, 2, 3 down to here, or then you have the D's and the S's, as we'll see in a sec. Things can become complex when you look at those transitions.
So I'm slightly confused. The circles, little dots, they represent the electrons or the shape of the orbit?
The circles represent an orbital, a region in space where we are likely to find an electron of a given energy. 90% likely. The electrons are represented by a slash through these circles. 1 slash means 1 electron. 2 slashes means 2 electrons. Okay?
Then why is there an electron for lithium?
So lithium has 1, 2, 3 electrons. Lithium is atomic number 3, so we have 1, 2, 3.
But would it really matter if it just like 3
How many electrons can each orbital hold? 2. Okay, so we can't put 3 down here. The next electron has to go into the next open circle. Okay? Now, remember I said, we talked about the, I gave you some, for L, I said L is equal to 0 to n minus 1. And remember we said these guys come as a set of 3, and we have to be able to tell them apart, right? Well, the m sub L values come from negative L, 0 to L. Integer values from negative L to L with 0. So when you have this, right, that's a p orbital. That has an L value is equal to 1, then your m sub L values are going to be negative 1, 0, and 1. And that's why there's 3 of them. Those are the rooms in the house. Right? Those are rooms in the house. Okay? And then if you had a 2, I hit the wrong button. Pardon. Yeah. So here with these, this is the D's, L equals 2, so you have negative 2, negative 1, 0, 1, 2, like that. Okay? And that's that pattern that grows. We'll spend a little bit more time talking about that. All right, now, here's what's important about this. What we want to be able to do is we want to be able to fill these up in order. Okay? We want to take the electrons and put them in these arrangements. Okay, we want to take the electrons and arrange them inside the atom, because how the electrons are arranged, where they are, is what determines the properties of the atom. How it behaves chemically, what it'll bond with, which, right, all that bonding stuff we need to get to, and how hard it is to gain or remove electrons. So there are 3 rules that we use to fill this type of diagram. Rule number 1. Pauli exclusion principle says no 2 electrons can have the exact same set of quantum numbers. No 2 electrons in the same atom can have the same set of quantum numbers. So that's where our m sub s comes in. So here, this is our 1s orbital, right? So what's the n value here? What's our quantum number n? It's the 1 at principal energy level. So that's going to be the 1, 2, 3, 4, 5, 6. That's our n value. Now, our s tells us that is the L equals 0 value. And when L equals 0, the m sub L value here, m sub L, can only equal 0. But remember I said I could put 2 electrons, 1, 2, into that box? Each orbital can hold 2 electrons. Each electron has to have a different quantum number. They can't be exactly the same. That's where the m sub s value comes in. M sub s, okay? And the m sub s is either going to be plus 1/2 or minus 1/2. Doesn't matter. One of the electrons is plus 1/2, one of them is minus 1/2. It's irrelevant which one is which. They just have to be opposite. We call that spin pairing. When you put 2 electrons in, they have to have opposite spin. Positive spin, negative spin. That minimizes their repulsive force. Because 2 electrons put into the same orbital is like 2 siblings put in the same room. They're going to fight more. Okay? Now, once you get 2 kids in one room, 2 electrons in one room, that's as many as you can fit. That's as many as it can hold. Okay? So what happens is the next electron that you add has to go into a higher energy state. So like this room is closer to the nucleus. What's the nucleus of the house? Kitchen, where the food is. So you want to be close to the food, right? This is an analogy, right? So the electrons will go to the lowest energy level closest to the food. Now you don't want, the further away from the food you are, the less likely, the harder it is for you to sneak down and grab a cookie. So the further away you are, the higher energy it is. The more energy it takes you to get, right? The further away you are, the more energy the electrons have. So the Aufbau principle, which is German for build up, says that you put electrons in the lowest energy orbital first. And you have to fill this lowest energy orbital with 1, 2 electrons before you can go on to the next one. And then you fill this one with 1, 2. What's my next energy level? What's the next lowest orbitals? 2 p's. Okay, but look, these come as a set of all the exact same energy. Okay, these 2 p's come as all the exact same energy. And this is where the third rule comes in, called Hund's rule. And Hund's rule, or the rule of maximum multiplicity, says that, hey, you want to put 1 electron in each orbital before you start doubling up. If you think of this as children going in a room, do they want to double up, or do they want to be 1 in each orbital, 1 in each room, before they start to have to share? So electrons go 1 in each room, 1 in each orbital, before they start to double up. So the first 3 get 1, 2, 3, each one gets its own orbital. Then you would start to double up 4, 5, 6. 3 orbitals in the p's, so a set of p orbitals can hold 6 electrons. 2 electrons in each orbital. Now, what's my next energy? I'm going to go to 3s, and I'd fill that up. And then I'd fill up these 3 p's. And then what's my next lowest energy? Well, let's look at this for a sec. Look at the picture. Yeah. If you look at this picture, here's the 4s's. They're just a tiny bit below the 3d's. So you go from 3p to 4s, then to 3d. Now remember, this is caused by that splitting. The more electrons, the greater these energy levels split apart. So the 4s fills first, then you fill the 3d, then you come back to the 4p. And what comes after the 4p? 5s. Then the 4d. Then the 5p. Then the 6s. And then you go, oh man, what the 4f is lower than the 5d. So now we got to throw those f's in there. And it's all this crazy splitting. And you go, this is a nightmare. How in the world am I ever going to remember all this stuff?
Wait, is 4F bigger than 6S?
4f is higher in energy than 6s. But lower than 5d. And notice that they're actually getting real close together here, and there's going to be this weird interactions and stuff. And so you say to yourself, this is crazy. How in the world am I ever going to remember this? And then you say, wait, the periodic table will save me. Okay? The periodic table will save me. And before we do that, I want to show you this quick clip. No, whatever. They stopped bugging me.
think atoms had electrons orbiting the nucleus, like planets orbit the sun. Now we know better. Instead, imagine taking many snapshots of an atom. You would find the electron at one location, then at another, and then at yet another. After a very large number of snapshots, you would see the probability of finding an electron at any point in an atom. This collection of locations is called an orbital. An orbital is often depicted by drawing a surface inside of which the electron is found 90% of the time. This particular surface, a sphere, encompasses the lowest energy orbital, the 1s orbital of an atom. Another way to visualize this orbital is to cut a slice through the sphere. In this representation, brighter colors indicate a higher probability of finding an electron at a certain location. Because the 1s orbital is spherical, these values depend only on the distance from the nucleus, not the direction. Either one or two electrons can occupy one orbital. The two elements with electrons only in the 1s orbital are hydrogen and helium. Lithium and beryllium atoms have electrons in the next highest energy orbital. The 2s orbital is spherical, like the 1s orbital. It's larger than the 1s orbital and has a nodal sphere where the electron is never observed. Although the probability of finding an electron is greater than or equal to 0 at all locations, the function that describes an orbital, the wave function, has both positive and negative regions. As a reminder of this fact, the green areas indicate positive regions of the wave function, while red areas indicate negative regions of the wave function. The next 6 elements have electrons in the 2p orbitals. Each 2p orbital points in a specific direction, unlike the spherical s orbitals. The surface encompassing the 2py orbital points primarily along the y-axis. A nodal plane, in which the electron is never observed, is located in the xz plane. The 2px orbital is identical to the 2py orbital, except that it points primarily along the x-axis. The nodal plane is the yz plane. The third p orbital, the 2pz orbital, has its lobes directed along the z-axis. The nodal plane is the xy plane. These 2p orbitals form a set of 3 that are equal in energy and can be occupied by up to 6 electrons. Sodium and magnesium, the next 2 elements, have their chemically significant valence electrons in the 3s orbital. Like other s orbitals, the 3s orbital is spherical in shape. It is bigger than the 1s and the 2s orbitals and has 2 nodal spheres. The probability of finding an electron in this orbital depends only on the distance from the nucleus, not the direction. The next 6 elements have valence electrons in the 3p orbitals. Like the 2p orbitals, there are 3 3p orbitals. Each of these orbitals points primarily towards the x, y, or z axes. Each 3p orbital has 1 nodal sphere, and every 3p orbital has 1 nodal plane. These orbitals form a set that can be occupied by up to 6 electrons. Potassium and calcium have valence electrons in the 4s orbital. The 4s orbital is larger than the 3s orbital, but is otherwise similar in shape. The 4s orbital has 3 nodal spheres. The next 10 elements, the transition metals, have valence electrons in the 3d orbitals. 3 of the 5 d orbitals look similar to each other. Each orbital has 2 nodal planes, and the lobes of these orbitals bisect the axes. The 4th orbital is formed by rotating the dxy orbital until its lobes point along the x and y axes. This orbital is named the dx squared minus y squared orbital. The 5th d orbital has a unique shape. Its 2 nodal surfaces are nodal cones. This orbital is called the 3dz squared orbital. These are the orbitals of the valence electrons of the 10 transition metals. The next 6 elements have valence electrons in the 4p orbitals. Like the 2p and 3p orbitals, each 4p orbital primarily points toward an axis. Each 4p orbital has 2 nodal spheres. It also has 1 nodal plane, which defines the position of its lobes. The 10 second-row transition metals have valence electrons in the 4d orbitals. These orbitals resemble the 3d set, with each orbital having 2 nodal planes. In addition, each 4d orbital has 1 nodal sphere. A 45-degree rotation of the 4dxy orbital produces the 4dx squared minus y squared orbital. The 4dz squared orbital has a nodal sphere, in addition to the 2 nodal cones that define its shape. The 14 elements in the lanthanide series have valence electrons in the 4f orbitals. There are 7 4f orbitals. Each 4f orbital has 3 nodal surfaces. The z squared y orbital is transformed into the z squared x orbital by a 90-degree rotation. The x cubed f orbital is related to the y cubed f orbital by a similar 90-degree rotation. The fxyz orbital looks like a d orbital with an extra nodal plane. A 45-degree rotation of this orbital forms the 6th f orbital, the fx squared minus y squared z orbital. The 7th f orbital, z cubed, resembles the dz squared orbital with an additional nodal plane. This is the orbital basis for the periodic table. Other orbitals can be generated just like those shown in this video. Atomic orbitals help us to understand the arrangement of all the elements and many various chemical properties in a logical fashion.